Good morning, students. Today let us study organoaluminium compounds. Okay. Now what are organoaluminium compounds? They are compounds which contain aluminum metal and the organic group. Okay. Now what exactly is the definition of organoaluminium compound? So these compounds in which alkyl or aryl groups are attached to aluminum, okay, which is the organic group, alkyl or aryl group. So that must be linked to or attached to aluminum metal. Okay. Now what is the general formula of organoaluminium compounds? R3Al, that means 3 alkyl groups and aluminum, 2 alkyl groups R2, aluminum and then chlorine, okay, 1 alkyl group R and then 2 halogens Cl2 and aluminum, or dimeric molecule. Dimeric molecule is just the double molecule of R3Al, dimeric, okay. Al is 2 twice, R3 that is, okay, R3 becomes R6, so Al to R6. So this is the dimer of R3Al, okay. Then another organoaluminium is R3, that means 3 alkyl groups, 2 aluminum and then 3 chlorine, okay. So these are some examples for organoaluminium compounds. Alright. Now how do we prepare? Okay. So what is the method of preparation? First one is from Grignard reagent. Now organoaluminium compound is obtained when a Grignard reagent is treated with aluminum chloride in the presence of ether. So ether is the solvent. Aluminum chloride is made to react with the Grignard reagent. What is the general formula of Grignard reagent? RMgCl. This is the halogen with Grignard reagent. Okay. Grignard reagents contain alkyl or aryl group, magnesium and then halogen. So halogen here taken is chlorine, that's all. So RMgCl plus AlCl3 in the presence of ether as a solvent, you get what? RAlCl2 and then MgCl2. Okay. Suppose we have 2 Grignard reagent molecules 2 times react with aluminum chloride in the presence of ether giving R2, okay, R2AlCl and then 2 times MgCl, that means 2 molecules of MgCl2. Suppose if 3 molecules react, 3 are MgCl, it will combine the AlCl3 in the presence of same solvent ether to give trialkyl aluminum R3Al, alright, R3Al plus 3 molecules of MgCl2. So these are the general equations for the preparation of organoaluminium compound starting from Grignard reagent. Okay, next slide. Now second method, from other organometallic compounds. When aluminum or aluminum compound is treated with other organometallic compound gives organoaluminium compound. So aluminum metal or aluminum compound, okay, treated with other organometallic compound. Which are the other organometallic compounds? Here dimethyl mercury, here phenyl lithium, pH is phenyl group and this also phenyl group, okay, lithium, phenyl lithium. So dimethyl mercury 3 molecules combined with the aluminum in the temperature 363 Kelvin. So heated to this temperature you get dimer of trimethyl aluminum, that is Al2Ma6 plus 3Hg. Suppose you take phenyl lithium, that is made to react with aluminum, that is boiled with aluminum in the presence of toluene, okay, toluene is the solvent. We get dimer molecules here also Al2PA6 and then 6 lithium, alright. And if you have dimer of aluminum, okay, aluminum, organoaluminium, that is the halogen here, dimer of halogen, that is Al2Cl6, okay. Monomer is AlCl3, dimer is Al2Cl6. So you get Al2PA6. So this will combine, Al2 and pH will combine, giving Al2PA6 and the lithium will combine with Cl giving lithium chloride. Okay. Third method is industrial method. Aluminum is alkylated by means of alkyl or aryl halide Rx in the presence of catalyst. So aluminum is made to react with alkyl or aryl halide in the presence of catalyst. Which is the catalyst used here? Traces of iodine, aluminum chloride or aluminum trialkyl aluminum. You get R3Al2Cl3. Alright, next slide. Now what are the properties of organoaluminium compounds? First property is aluminum trialkyls and triaryls are volatile liquids or low melting solids. So these are the physical properties. So aluminum trialkyl and triaryls are volatile liquids and having low melting points. Okay, they are highly reactive, burn in air and react violently with water, and that means vigorous reaction with water. Then a reaction with the protonic reagents. So what are the chemical properties? So first property is reaction with the protonic reagents. Protonic reagent, which are the protonic reagents? Water, hydrogen halides. Okay, so this contains proton, correct? So water contains proton, hydrogen halides contain protons. So this organoaluminium compound react with the water, that means proton containing compound. Similarly react to hydrogen halide, which also contains proton. Okay, this is the dimeric molecule. Okay, Al2R6 dimeric molecule, Al2R6 combine. Here it combines to give aluminum hydroxide. Okay, and then RH. What do you mean by RH? So R and H will combine. This will combine giving RH. Aluminum will combine with hydroxide giving aluminum hydroxide. What is RH? Alkane. General formula for alkanes is RH. R is alkyl group. Okay, if it is a methyl group, methane you get. CH3 and H is CH4. Okay, correct. And suppose you have C2H5 as alkyl group, you get C2H5 and H, that is C2SS, ethane. Okay, so depending on R alkyl group, you get different members of alkane series. Alright, so if it is combining with the organo, that is aluminum compound, if it combines with the HX, okay, that is hydrogen halide, X may be any halogen, giving what? AlX3. Okay, so here bond will break, Al will combine with the X giving AlX3. This R will combine with the H giving what? RH. RH is once again, it is what? Alkane. Correct? Alkane. RH is nothing but alkane. Okay. Then next chemical property is reaction with the lithium alkyl. Aluminum alkyl reacts with the lithium alkyl in the presence of benzene to give mixed alkyls. So triethyl aluminum reacts with ethyl lithium in the presence of benzene to give one tetraethyl lithium aluminum. Okay, so this is a compound, additional compound is formed with the 4 ethyl groups. Okay, next slide. Next chemical property is reaction with halides of less electropositive elements. Now halides of less electropositive elements, which are the halides of less electropositive elements? Boron, for example, calcium, silicon, okay, tin, etc. These react with the aluminum alkyls and their respective organometals are formed. So these will combine with the aluminum alkyl to give one respective organometals. So example, trimethyl aluminum, okay, combines with boron trichloride giving boron trimethyl boron. So this will combine boron and trimethyl, this bond will break here. Okay, so boron and trimethyl will combine to the trimethyl boron and aluminum will combine with the chlorine to give what? Aluminum chloride. Alright. Similarly, trimethyl aluminum combines with the calcium chloride. Okay, same type of reaction. Calcium will combine with the 2 methyl groups giving dimethyl calcium. Why? Because calcium valency is 2, therefore it will combine 2 methyl groups. Aluminum boron valency is 3, so it combines with 3 methyl groups. So that depends upon the valency. Alright. So trimethyl aluminum combines with the calcium chloride giving dimethyl calcium and then aluminum chloride. Next chemical property is reaction with other organic ligands. So it will combine with other organic ligands. So aluminum alkyl readily reacts with other organic ligands forming adducts. Adduct is nothing but addition product, and thus AlR3 behaves as a Lewis acid. Lewis acid means it accepts a lone pair of electrons. Okay, what is Lewis acid? What is the definition of Lewis acid? It accepts a pair of electrons. Okay, so AlR3 is a Lewis acid. It accepts a pair of electrons from the ligand. L is the ligand, okay, which is nothing but a base, giving what? Addition product AlR3, where L is amine. L may be amine group or phosphine group or ether or thiether, which must be able to donate, in a position to donate a lone pair of electrons. Okay, next slide. Next property, alkene insertion reaction or growth reaction. What do I mean by this? alkene group is introduced into the product molecule, okay, to the reactant, so that you get product. So since alkene group is introduced, you will get a long chain. So it is nothing but growth reaction, growth of the chain taking place, okay. That's why it is also called growth reaction. Now let us see what is the example, how it reacts. So when AlR3, that is the trialkyl aluminum, is treated with ethene, okay, ethene is nothing but unsaturated compound alkene at 425 Kelvin and 100 atmospheres pressure, okay. This is the pressure and this is the temperature. Ethene is inserted to the aluminum carbon bond of monomeric AlR3, giving long chain derivative, okay. Now how do you write trimethyl aluminum? If you split up and write trimethyl aluminum, you will get like this structure: aluminum 3 valency, okay, 3 methyl groups are there, combines with 3 molecules of ethane. C2H4 is nothing but ethane, CH2 double bond CH2, okay. So CH2 double bond breaks and single bond is formed, and then that it gets introduced into the chain, okay. So you get here alkene insertion or introduction of alkene, CH2. Similarly here also alkene group is introduced, okay, 3 molecules are reacting, okay. So CH2. Here also one more molecule adds here, so that you get CH2CH3. Alright. Suppose you have n molecules, okay, 3n molecules reacting alkene, okay, 3 times n molecules of alkene reacts, so that you get CH2, okay, CH2 n times a long chain, that's why it is written as n times CH3. Similarly here also CH2 n times, okay, CH3. Here also CH2 n times CH2. So this is long molecule, okay, long, that's why it is called growth reaction. Long chains of length 14 to 20 carbon atoms can be synthesized. So how much long length? 14 to 20 carbon atoms, okay, synthesized industrially in this way. So in industrially we can prepare 14 to 20 carbon atoms long chain molecule. Then they are converted to unbranched aliphatic alcohols, okay. So after that they will be converted to aliphatic alcohols, which are used in the synthesis of biodegradable detergents. Why these aliphatic alcohols are required? To synthesize what? Biodegradable detergents, alright. So this is the reaction. So trialkyl aluminum trialkyl are 3 times 425 Kelvin 100 atmosphere, you give trialcohol, okay, that means 3 molecules of alcohol you get on hydrolysis. So 3 are CH2OH, okay. Next slide. Now what are the applications of organoaluminium compounds? Used as, so organoaluminium compound are used as Ziegler-Natta catalyst for the polymerization of olefin and diene. So Ziegler-Natta catalyst is used in the polymerization reaction of olefin is nothing but alkene and dienes. So what is Ziegler-Natta catalyst? It is a mixture of organoaluminium compound and transition metal compound, okay. Now which is the organoaluminium compound? Triethyl aluminum. Which is the transition metal compound? Titanium tetrachloride, okay. So Ziegler-Natta catalyst nothing but a mixture of titanium tetrachloride and triethyl aluminum, okay, that is used as a catalyst in the manufacture of high density polymer. That's why it is very important. Used in the preparation of other organometallic compound, that is another application. Used in the manufacture long chain alpha alcohols, okay. In the previous example you have seen previous chemical property, you can get what? Long chain alpha alcohols. In the dimerization of olefins and manufacture of higher linear alpha olefins, okay. Now what is the structure of organoaluminium compounds? So this is the dimer molecules Al2Ma6 and Al2Pa6, so that exists in dimeric form. So aluminum 2 methyl groups, okay, one aluminum having 2 methyl groups, another aluminum having 2 methyl groups directly linked, and then in between that there is a bridge also with the one methyl group CH3, okay. So AlCl3 and another aluminum have got total altogether AlCl3, okay. That's how you get Al2MeCH6, okay. Similarly Al2PS6, one aluminum has got 3 phenyl group, but one is bridge, okay, bridging group, that is phenyl group in between the 2 aluminum metals, okay. So pH, and this is the bond length 195 picometer. Here also bond length is 195 picometer, bond angle is 78, here bond angle is 77 degrees, okay. In both of these compounds, there are 4 terminal aluminum carbon bonds. So, there are 4 terminal aluminum carbon bonds and 2 aluminum carbon aluminum bridge bonds. So, these are aluminum carbon aluminum bridge bonds. Okay. So, there are 2 bridge bonds, one this is one, another one is this. Okay, one is top like this, another one bottom like this. Okay. So, there are two bridge bonds. And how many terminal aluminum carbon bonds? 4. How it is 4? 1 here, 1, 2, this side 3 and this side 4. Okay. Terminal 4 bonds are there, bridge bonds 2 are there. Okay. In both cases, aluminum carbon bridge bond distance is longer than terminal aluminum carbon bond. So, this bond length is longer than, bridge bond length is longer than terminal aluminum carbon bond. Okay. Next line. Aluminum carbon aluminum bridge bonds are 3 centered 2 electron bonds. So, these are 3 centered 2 electron bonds. Okay. That means 3 atoms are there, but electrons are only 2. That is called 3 centered 2 electron bonds. Alright. They are formed by the overlap of sp3 hybrid orbital of carbon of CH group containing 1 electron. So, how they are formed? sp3 hybrid orbital of carbon. Okay. sp3 hybrid orbital of carbon of CH group containing 1 electron. Okay. So, this will overlap with this aluminum. Okay. This will overlap with this aluminum. So, this is 3 center 2 electron bond. Okay. Next slide. Now, let us study another compound, organomercury compounds. Now, what are called organomercury compounds? These are compounds in which alkyl or Rl groups are attached to the mercury. Okay, alkyl or Rl groups are attached to mercury. They are called organomercury compounds. What is the general formula? RHGS. Mercury is linked to organic group R. Okay, and then halogen. Okay, here alkyl group or Rl group is linked to mercury R2Hg. Preparation. Now, how it is prepared? Starting from Grignard reagent. Alkyl or Rl mercury compounds can be prepared by treating Grignard reagent with mercury chloride. So, Grignard reagent. So, this is similar to one the organo aluminum compound preparation. So, RMgX made to react HgCl2, RHgCl and then MgXCl. Example is R you consider as C2H5. Okay. CX you consider as Cl. So, HgCl2, C2H5, HgCl plus MgCl2. RHgCl, another example RMgX. Okay, RMgX. You get R2Hg, MgXCl. So, okay. Example is R you consider ethyl group, and then here also R you consider ethyl group. Therefore, you get diethyl C2H5 2 times. Okay, Hg plus MgCl2. Next line. From alkyl halide, another preparation, alkyl halide and mercury. Alkyl halide and mercury react with each other. You can see here Rx. Alkyl halide and mercury react with each other in the presence of sunlight. Okay, made to react in the presence of sunlight. You get one RHGX. This is addition product formed RHGX. So, example is R you consider as ethyl group. Okay. And then X as iodine. In the presence of sunlight you get C2H5HgI. Another method, by direct replacement of hydrogen by mercury. When alkane, what is the general formula for alkane? RH. Alkane or benzene is treated with mercury. So, in the hydrogen of alkane or benzene is replaced by mercury and organomercury is formed. So, alkane general formula is treated with mercury salt. Mercury salt is HgX2. Okay, giving what? RHgX plus HX. Another example is R you consider as phenyl group. Okay, PH, and then diacetyl mercury. So, you get one phenyl group introduced here, PHHG OAC HOAC. Okay. Next slide. Now, what are the properties of organomercury compounds? RHGX are crystalline solids. So, organomercury compounds are the crystalline solids, and mercury alkyls are volatile toxic liquids. So, since mercury is present, these compounds are toxic in nature and thermally stable to a considerable extent. All of the alkyls except dimethyl mercury decompose on standing to metallic mercury and hydrocarbon even at room temperature. So, they decompose even at room temperature. Okay. These are known to be light sensitive because of similar electronegativities of mercury and carbon. The mercury carbon bond is essentially covalent. These compounds are almost inert towards air and moisture. Okay. This means that mercury carbon bonds are not easily cleaved by water or bases or acids. Next slide. Mercury alkyls or aryls react with halides or more electronegative elements, forming new organometallic or organometalloid compounds. Now here are equations. So diphenyl mercury reacts with the silicon tetrachloride, giving trichlorophenyl silicon. Okay, and then chlorophenyl mercury. Similarly, diphenyl, here two molecules react with silicon tetrachloride, giving diphenyl compound, here monophenyl compound, one phenyl group. Okay. Triphenyl compound, three molecules react with arsenic. Okay. Trichloride giving triphenyl, okay, arsenic, and then monophenyl mercury chloride. So this is diphenyl mercury, boron trichloride giving phenyl dichloroboron. Okay, this is the compound formed. Similarly, two molecules of diphenyl combine with the antimony trichloride, giving triphenyl compound, monophenyl compound, and then mercury. Okay. Next slide. What are the applications of organomercury compounds? Dimethyl mercury and monomethyl mercury halide, that is MEHGX, is used for treating seeds against fungal attack. Okay, they are used in the treatment of fungal attack for seeds. Then phenyl mercury acetate is used against apple scab, a fungal disease of the leaves and fruit, and also to kill crabgrass in lawns. Then some of the mercuries are also used as powerful diuretics. Then methylate and metaphor and mercurochrome are used as externally as antiseptics. And methiotate is, what is methiotate? It is sodium ethyl mercury thiosalicylate. Metaphor is used is 3-hydroxy mercury 4-nitro-orthocresol anhydride. Mercurochrome is merbromine 2,7-dibromo 4-hydroxy mercury fluorescein. Okay. Now structure and bonding. What is the structure and bonding? So dialkyl or diphenyl mercury and monophenyl or monoalkyl mercury halide compounds contain linear RHGR or RHGX units. It is due to sp hybridization of mercury. So in these compounds, okay, mercury undergoes sp hybridization. In some cases, polymerization takes place to achieve linearity. Okay, so example is given, orthophenylene dimer. So this is a dimer, two phenyl groups are there. In between that, two mercury linked. Okay, like this, as a just like bridge bond. Sometimes trimercurization also takes place to maintain linearity of carbon mercury carbon. Sometimes what happens? Three mercury atoms bonded together with three phenyl groups. You can see here orthophenylene trimer. Okay. Now I will stop at this stage. Alright. So please go through all these slides. Okay. Any difficulty, please contact me. So when the offline classes starts, I am going to do this. Okay. Once again. Okay. So any clarification, please meet me. Okay. In the department. Alright. Thank you.